think that's fine. Hello, welcome to Math 2504. I hope I got the code right. My name's Paul. My name's Paul Billette, full name, because we've got two Pauls on this course. Yeah, this is the third year we've run this course. So I think we've been lulled into a false sense of security. So like all the tension of the first 2 years and good preparation will fade away. Hopefully this works. Yeah, so why are we doing this course? What's the purpose? Is when you go out and to get a job later on, lots of people end up using programming in their careers from mathematics. It's really common, lots of people I work with. But also it's a good tool in itself. And typically in your undergraduate maths education, it's like being weak. When I went through maths as an undergrad a long time ago, it was like you were just sort of expected to learn how to program by osmosis somehow. They'd give you an assignment, you write some horrible scripts, but no one ever taught you how to code. So you get to the end and then depending on where your career goes, you can have a pretty rough experience going out and then going on later on. And lots of things I wished I'd known, like it's a good focus for your mathematical education as well and gives you lots of tools, a good toolkit for your, even if you go into a research career, it's really useful. Okay, so what are we doing? How is this course run? Okay, so we've got, hopefully you've all seen the course website. Everyone seen that one? Yep, cool. We've got the course schedule. You guys will be more across this than I am, but we've got the lectures Mondays and Tuesdays. Thank you for coming at such a late hour. It helps. I'm from industry, Andy's from industry. So kind of we get an opportunity to come in and actually do this with you guys. So thank you for being accommodating with the time. I understand it's pretty difficult. Yeah, so Mondays, 2-hour lecture today. Then on Tuesday, we've got a 1-hour lecture from 6 till 7. We've got 2 pracs this year. There's a standard prac. See this here, standard prac, A, B, 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 blah, blah. And there's also a support practical. This one's, if you first one's, compulsory, second one's recommended. Particularly if we understand when you come into a course like this, we're going to have like 2 populations of students. There's going to be some who've like haven't wanted to touch programming until this point, and they're going to have, a bit of an interesting transition into doing this stuff. And other people who've been programming since they were 8, they'll be better than me. They'll have a good time talking to Andy. And those trying to match up that, syncing up those 2 populations, it's nothing wrong with, why would you do the course if you already knew how to do it? So it's fine to be started at a low point. That's what we're expecting with this course. So, we'll give you lots of help. So we're adding the extra support practical. So recommend that you come along to that. We also have the consultation hour on Wednesday from, I think Yoni said it was 7:30. So that's good. So I guess we can introduce the staff now. Everyone's happy with that. My name's Paul Billette, I said that. I'm probably the least interesting person here, so I'll pass across to everyone else to introduce themselves. I don't think you're the least interesting. I'm the first. They'll get sick of me quickest.
Don't worry, you can't get sick of Paul. My name's Andy Ferris. Yeah, the camera's over here. Yep. So my name's Andy Ferris. I'll be lecturing a few times later in this course. So Paul will be taking the first third of this course, I believe. You can see the schedule up on this board here. And I'll return to get into some more details into Julia and then to talk about event simulation and data and stuff at the end towards the end of the course. And I'll speak more about my background and such then. But yeah, pass it over to Yoni.
Hi, I'm Yoni. I'm the course coordinator. I see a few faces from the boot camp and some new faces. Just these guys underplayed themselves. So Paul and Andy, they've worked together for a long period and 2 companies at least in industry. And now they work in separate places. So this is their joint workplace. Yeah, and this is now the 3rd year we're running the course, and I just thought they're so cool. So I want to be like them, and I also changed now to 50% industry. So I'm an associate professor, but I'm 50% working also in industry, in pharmaceutical modeling. You'll hear about each of ours kind of career paths as we go through the course. And also just mention that we are going to have Megan and Matha and Anna, and they'll each give perspective seminars. previous year's students found those perspective seminars useful. Okay, so that's me, and probably you want over to Paul Verbeek.
I'm here. Can you hear me?
Hear you now, Paul.
Can everyone see me? G'day, I'm Paul. I'm from the Electrical Engineering and Computer Science Department. I'm going to be coming in later on in the course to teach you some computer algebra. So I have a PhD in computational algebraic geometry. If you ever heard of programs like Maple or Mathematica or Magma, I'm going to be teaching you all of the underpinnings of those systems. So it's going to be quite fun. In the past, some of the mathematicians have told me that it was one of the first projects where they really enjoyed programming because they were programming math. So I'm excited to get to know all of you, I think in week 7 or 8. That's all I gotta say.
Cool. We also have some tutors for the course. Are they already in, or are they all online? Online? If you want to introduce yourself. Silence is deafening.
All right, I guess I will start. Hi, everyone. My name's Elaine, and I will be taking one of the support practicals on Friday at 9 a.m. And I've tutored this course for the past 2 years. So I think I have a good idea of where people tend to struggle a little bit more, or the things they find easier. So hopefully I can be helpful in that support prac. Just to let you know a little bit about myself, I'm doing my PhD at UQ at the Institute of Molecular Biology. And within that, I'm working at the Center for Cellular Biotechnology. So I use kind of like simulation guided approach to optimize systems. And I work a lot with Julia in my PhD. Yeah,
Thanks, Elaine.
that's me.
We got any other tutors online?
I'll go next.
Cool.
My name's Lee. I took this course last year, and I'm in my 3rd year of a maths degree, majoring in pure maths at the moment. I'm interested in using code to visualize maths concepts programmatically, and I also like to dabble in a bit of competitive programming. I'll be taking the Wednesday normal practical at 11 a.m. So you can find me there.
Cool. Any more?
Yeah, I guess I'll go next. Hi, my name's Cooper. I took this course last year as well. I currently am in my undergraduate, doing math science. My interests are statistics and genetics. So you put them together to get bioinformatics. That's a lot of computing. I take the Thursday 1 o'clock practical. Be sure to come along. It'll be a lot of fun. And I'm hoping I can help you enjoy coding as much as I do.
Oh, thank you. And it was last time was Isaac, right? We've only got, is that the 4 tutors? Yeah, or is there any more?
That's right. I'm here.
Oh, hello.
Cool. Hello. Hi, my name's Brandon. I've recently graduated from my Bachelor of Mathematics with a major in data analytics. I'm taking the Thursday support practical at 5 p.m. So I'm super pumped to help people in just kind of get a way around Julia and help you guys. So keen to see that.
Cool. Any more now? It's like a cloud's coming out of a car.
Yeah.
Hey.
Hello, my name's Lamau. I took the course last year as well. I'm doing a maths and computer science degree in my 3rd year. And I'll be taking the Wednesday 9 a.m. practical, I believe. Yeah, my interests are in statistics, which is what I'm majoring in. I also did an internship at Fugro at the end of last year. So I got the chance to work with Megan, who will be coming along for that first perspective seminar. Yeah, that's me.
Yeah, more? Who's next? Who's any more online?
Isaac couldn't make it, but he did write something,
Oh yeah, Isaac.
a
Yeah.
message.
Yeah, so Isaac was a really good student last year. I can remember him he's got a web page listed that, so if you know it, so you can know what he looks like. Yeah, and kindly link that. Isaac, where are you? Come on. That's slow. Anyway, yeah, so Isaac took this course last year. He was a really good student. That's what he looks like. He's got his own webpage. He majors in statistics and physics and enjoys making simulations of what he learns in his statistics lectures. He'll be taking the normal practical at 5 on Wednesdays. So that's Isaac. Yeah, so 2 more, okay.
Yeah, so there's just, so also Alistair. So Alistair is doing Friday at 1 p.m. Alistair is also, as Elaine, he's doing a PhD, uses Julia also in his PhD in applied math. And there's Nazif. Nazif is also was a student last year. So we have now, in contrast to previous years, we have a lot of tutors that did the course last year. So actually, they might know the course better than all of us. We never did the projects. They did, and you will too. So Nazif will do Thursday at 11 a.m. He's doing computer science and mathematics for his degree.
Cool. All right. That's through everyone. So let's go. Yeah, so back to the course. Again, I'll just reiterate that consultation hour because it's like, that's like free to corner the lecturers. You got to stuck there for an hour on a Zoom call. So if you're stuck for questions, really use it. Not as many people as I would have expected come along to those ones, particularly if you're having like, you know, things you might be a bit embarrassed by, like just simple setup problems and things like that. If you're struggling to get your environment set up, you know, we'll be able to help you out there. So please feel free to come along to that with any questions you've got. Make use of the resources you have. Any questions on that so far? No. Good. Okay. So first thing for assessment, you have this big homework thing. So this can be a bit of a baptism of fire. It's like your first big project. If you're new to programming, it's like going to be a bit of an experience to get up to speed with this one. You're learning, it's like for some people, you're just learning a new language. For some people, you're learning how to program and learning a new language. So that's going to be a little bit trickier. So please get started early. Please find a partner as quick as you can. Ask for help if you're struggling to find a partner. I think Yoni gave some good advice about having a lead, you know, someone take the lead on each question, but there's kind of, I always think of it as a non-negotiable amount of suffering to learn stuff. Like you have to do it. Like, so if you outsource one question to someone else and you don't go through them, you know, you don't engage with it yourself, you're never going to learn it. Programming sort of really is like that. Unfortunately, you really have to engage with it and do the work. It's like to get there. It's the same as these lectures. Like we've got all these lectures online. We've got previous years lectures online on YouTube as well. So you could shortcut and go through that. But again, you got to go through stuff to get it. Like there's no, you know, it doesn't work by osmosis. You have to just mechanically go through these things to pick it up. That's my #1 recommendation with these things. Cool. All right. So who has used Julia before? Is this first time? Has anyone used Julia before? It's probably a smaller set. Yoni has. Andy might have. Any of the students? Brand new. Who's used Python? Do you like Python? It's hard to not like Python. I think it's like the Toyota Corolla of programming languages. It's like it just does what you want. It's fine. It's kind of easy. Any other ones? Does anyone use C? Got a few. Anything more exotic? Can home here? See if we get a message. Chat. Oh, yeah, cool. Back in action.
Maybe you need to share screen. Here,
Oh.
sorry.
Cool.
No, didn't work. I didn't share. It's funny that during COVID and previous years, we
Yeah, it
were
worked
okay.
perfect.
Now it's
Worked perfectly with that.
all right.
Okay. So hopefully this, yeah, so using productivity languages so they can develop quickly. But, you know, you get to this thing where you've got an algorithmic bottleneck, you need them to go fast. You end up having mathematicians working with hardcore C programmers and having fights, but so get to the new age and there's like, these things are getting better and Python's getting better all the time. So don't think of this as a weird excursion into a weird language. It's an opportunity to learn a new thing. All these skills are transferable. I quite like Julia. We'll see how you guys get along with it. Okay, layout of the course. We have everything as on here. I'll roughly follow this. I won't go too far off piste, hopefully. But what we're going to cover for my section, we're covering units 1, 2, and 3. And I'm going to start with basics, a little bit on algorithms, a little bit on numerics and data formats and stuff. So as a nice intro, we've got a little problem of, I'll get this terror of having to go up to a thing and do a live coding demo. This is really, really intense. So we'll see how this goes. We'll do a little demo of some sort of useful problem you might do in Julia. So, okay, I'm going to enter a Julia session. Has everyone downloaded Julia yet? Everyone started a Julia REPL session? If I say a REPL, do you know what that means? Anyone doesn't know what that means? So that's a read, eval, print loop. So this is this Julia session. It's just like it's like a forever loop where it waits for your input, runs the code. I tend to use the Julia REPL all the time. That's what this thing is. So if I'm saying REPL, it's this read, eval, print loop. So it'll read your input, evaluate it, print, and then loop through it again. So this is the Julia REPL. Cool. So the first thing we were going to do is we were going to do a program to find, I'm going to show you some syntax. Again, I'll say you don't learn by osmosis, but I'll try. I'm not going to do a whole lot of syntax to start with. I'll just show you a little program and we'll see how it goes. So if we have, say, an array of data, so it's the first time I'm going to put some data in, 1, 2, 3, 4. Okay. This is like a stupidly simple thing, but we're going to go like, how do we find the max value in the array? And it's a simple program to start with. So you'll see a little bit of syntax. I'm writing this thing called function. It's like demarcating a little block of logic that we're going to do. Find max. And this syntax with the little parentheses is that it takes an input. So you put your inputs here. So we're going to say find x, find max. Current max equals minus inf. So this is setting the current value of the max to minus infinity. So if I didn't have that in the function, I'm setting a variable to current max to minus infinity. So if I have some value is 2 greater than current max, what's that going to say? True. Cool. So function find max x current max equals minus inf. Now we're going to take this array and we're going to loop through all the bits, compare it to the current max for x in x if this x greater than current max, we can say current max equals this x. We end the conditional statement. So when you're going like if, do this thing. So if this x is greater than current max equals this x. Then we're going to finish the for loop. And because Julia, the last line is the return, but sometimes it's better to be explicit. This function is going to return the current max. Now this is the moment of sheer terror where I run this thing and I see if it actually works. Okay, so that's pretty boring, you know. That's just, what would a test be that this might actually work? Let's put them out of order and put some random garbage in there. Okay, find max x, 4, still finding 4, so that's a good sign. Let's change 4 to 5 just to check, so I don't trust myself that it's doing the right thing. Oh, got it. 55 will do. 55, okay, cool, that's pretty boring. You might want to know the max in array, that's pretty useful, but Julia has a built-in function that's, you know, you can to do this anyway, that's much more efficient. Anyway, what we're interested in here is if we have some random data. So you're going to see this one in the notes, using random. This is a package, a module that we're going to load into Julia that lets you evaluate random numbers. So let's say we're going to draw 100 random numbers from a normal distribution. Or let's go unit interval because that makes more sense with the analysis given in the notes. Okay, we've got 1,000 random elements. This one's a bit less trivial. You can't just see what the answer is. If we're going to go find max, it'll say some number close to 1, which is kind of what you'd expect. Now, the interesting bit of maths, is this one, I'll let you think about it for a second, is how many, for an array of a given size, if we've got uniformly distributed numbers between 0 and 1, how many times are we going to find a maxima as we go through the array? So that's less trivial straight away, right? Like to do the analysis, this is me, I'm old, I'm over 40 now and I'm dumb. I can't do the analysis as well as I used to, but I can write it on a computer really quickly. So it's kind of like a magic power there, but it's only ever going to be approximate. So there's this tension between the two of like, we can do this thing quickly, the analysis might be hard. So let's modify this find max function. Oh, maybe this isn't the easiest way. Current max, going to add another variable, count max equals 0. So this is a bit more nicely syntaxed. I'm too lazy to write it out properly in the REPL, but count max plus equals 1. And now we're going to return two things, current max and count max. So I went pretty quickly there. So I'm starting the initial counter at 0. Every time I find a max, I'm going to increment the counter. That's pretty trivial. So now if I run find max, I'm going to get two numbers returned as a thing called, I'm going to call it a tuple. Anyone heard of tuple before? People nodding, good. I'll say things like this. If I say something that's a bit jargony, just go, hey, I don't know what the hell that is for. So we found 7. So we can run this a few times, because this is a random algorithm. I'm putting the semicolon there to suppress the output, just so it doesn't fill up the screen. If I run find max, this time it found 10, 9, 9. So we get this idea, 7, 5. So, there's a distribution over answers. Cool. Okay, skip to the notes. That's pretty much what this code here is doing. They might have been implemented a little bit differently. So basically the same. So I just went, the only bit of syntax difference here is that n equals n plus 1. I did a funny little thing where I went count max plus equals 1. So it takes the value, increments by 1. Same thing, does the same thing. Any questions on syntax so far? Understand the function? Yo. Plus, no. Yep. Cool. All right. Cool. That's easy. So next bit is a bit of the analysis about how we might go, mathematicians in training. How would you get this answer as an analytic expression? So this is, we'll probably get, in this notes, we'll give the expression for the expectation, not the distribution. Anyone's really smart, they can go and work out what the distribution is. I don't actually know what the answer to that is, but maybe Yoni does. They're randomized on the distribution of the draws. Yeah, so there might not be an expression. So this is one of these things is like, we can do a simulation, derive an approximate expression for the distribution, whereas analysis might fail you. It's really easy in maths. It's like, it's one thing it took me a long time to realize as I was going through my maths education is there's lots of stuff that's just really hard to solve that's easy to state. Like they will steer you through this narrow path of analytic results and stuff, but most of them aren't like that. Like numerics is the recourse to doing things in the real world nearly all the time. It's pretty tricky. So in terms of maths, we can think of setting up an indicator function that goes like, okay, we got some records xn, and we're going to have this indicator function that goes like, it's 1 if it's a new thing, it's 0 otherwise. And we're interested in the expectation of this thing, which is because expectation is linear. If identically distributed, independent identically distributed, we can say the expectation is linear. So because we're drawing random numbers between 0 and 1, think of the first record. What's the chance that's the new best for the current max? What's the probability for the first record in the 1? Yep, exactly right. So it's the first one, it's the biggest one. Then we go, okay, what's the expectation what's the probability distribution of generating the records as we go through? It's this series of 1 on I as you add more records. So you go through this. Yeah, that's the point as well. This is really important and goes to Yoni's point. For statistically independent identically distributed data points, you're going to have this, that the probability that I equals 1 on I. So if you're up to 10 points, 1 on 10, 100 points, 1 on 100. You want to sum all those guys up, which is this harmonic sum. And this really easy, trivial thing to say is it is known that. This harmonic sum to finite terms. Well, what's this going to do as we go to infinity, just to make it a bit more mathsy? Is it going to have a expression or is it going to be divergent? Divergent, yeah. So, but to finite terms, there's this known result that it's like log n, gamma, order 1 terms, where gamma is the Euler-Mascheroni constant. It's like, that's one of these special magic numbers. And as n goes to infinity, the order 1 terms vanish as n goes to infinity. So a bit more functionality here. I don't know how much of this I will redo on a REPL session, but we'll do it anyway. We'll do a little bit. So using plots. So this is slow. Did I start Julia 1.9? I did. Anyway. Not as fast as I would say. Okay, so plots is a plotting library for Julia. Gives you the basic stuff you'd expect to do. So if you're going to go plot, 1, 2, 3, 4, you know, you're going to get these plots. There's lots and lots of formatting options. We'll talk a bit about that later in the course. You'll get a bit more of experience. So math constants. I don't know if I added that guy. Anyway, we've got a thing here where we're going to do a Monte Carlo simulation of like, how does the error in this term, sorry, I'll just minimize this completely while I look at this. How does the error in this approximation diminish as we go to larger and larger terms? So a little bit of syntax here, special things we can do. So this guy is an inline function where we're defining the function in one line. We're going to say h of n equals, this is something you can do in Julia, write it in one line. It's equivalent to writing out the long-winded version of this. So we can evaluate this guy, h of n of 10, it's 2.9, equivalent to going the more long-winded one, h of n. You could go, you could do this accumulator thing I did before. So you could go count equals, y equals 0 for I in 1 to n, I in n, 1 to n, y plus equals 1 on I. So, you can do long-winded stuff. I won't even check if that's true because I'm just likely to set myself up for failure. But this is just a nice little inline version of the same thing. So it's much more compact representation. We can write the functions out. You'll see more and more of this. I just thought I'd show you. So instead, we can use the built-in Julia sum function that goes for I equals 1 to n, blah. Okay, so this little bit of plotting here, we'll go through this to 1 on n, and we can see what the error in the approximation is by using the Mascheroni constant, this expression up here. And see that that's reducing. Now this is...
Could you explain the steps in the maths?
Yeah.
So when it says the probability of I equals 1 is 1 over I.
Yep.
Why is that true?
Well, okay. Anyone want to have a go here? I'll pass it around to the class. Yep.
expect that probability follows that 1 on I formula, where it's always like the next one is half is likely to be the record, 1/3 is likely, so on and so on. Then the expected value of so and so has to be the same as the probability, because you're expecting, well, it's binary, it's either 1 or 0, so it has to be probability.
Because it's uniformly distributed between the interval. So first one, you guarantee that it's the biggest. Second one, you randomly pick from a uniform interval, you get 1 on I. Hope that makes sense. We'll talk. Okay, cool. All right. So this is the bit that's probably more interesting, is like, again, make this point, analysis is hard, simulation is kind of easy. We can do a Monte Carlo simulation where we're going to go, let's just do this lots of times and we can see what the distribution of this thing is. So again, I won't sit here and run through it in case it's a big number, a big thing, but we're going to go through this. And so we're going to go from S in 1 to 10 to the 5. So lots of samples. This thing, random seed. So S, so we're choosing a new random seed for these random numbers every time we do it, just to guarantee we don't generate the same array. So this is one using random. I've got that random dot seed. If I seed the random number generator, oh, I can't type. If I go draw a random number, if I set the random seed again, I'm going to get the same random number every time. That's because all these this is going to talk about this later in the course. I think Andy is going to talk about it quite a bit later on about random number generators. They're all pseudo random number generators. They're generated with an algorithm. Part of the algorithm takes state and generates a random number from that. So something useful. They're not really random numbers. What I'm saying is, so this really useful property of setting the random seed, you can sort of guarantee, make some pseudo guarantees about whether you're going to get a different set of random numbers or not. So the whole purpose in this bit of the code about setting the random seed to a new number in this interval every time is just making sure we don't get the same random number, draw 100 data points, run our find max function, push this into this records array. So this another little bit of Julia syntax. If we have something like records, this will be an empty array of type any. Talk about types later on. If I push something to records 2, now I look at records. If I push another number. So what it's doing is constructing this array one at a time. So you push onto the array. We can see how many times we found a new max every time we ran this function. And then we can make a histogram of the records. So this is the complicated bit. So we've got an approximate expression for the expectation. That was a little bit hard, not that hard. We can actually simulate the distribution of this thing. So that's even more powerful. So hopefully that makes sense as like something useful you might want to do. Cool.
Why does that push function have the exclamation mark?
Because this is a bit of Julia syntax. If you're editing your input, you put an exclamation mark there to remind yourself that you're doing it. Side effect, yeah. Oh, yeah, that's pretty much the way to think about it. So it's kind of a convention. Like when you're naming functions yourself, you don't have to do this, but it's a thing you do, just as like, yep, that's the whole point. So push is mutating records, or it's putting an element in records. So you give this hint that you're doing that in the function call. Any questions on that little simple demonstration? No, it actually is. I'll try and link it up to something a bit more useful. I won't go too hard on that. I won't do that. Okay, I'll just leave that be for the moment. Okay, cool. So that's it. So this is just a little bit of, show you a nice gentle introduction to Julia syntax, see a little bit of code, see something semi-useful you might want to do mathematically. So what we're trying to do with 2 points in this course is we want you to learn some new interesting math side of programming. I think the math side of programming is really interesting and really useful. Historically, it's super interesting because it's like where it kind of came from. Programming is the big impetus for developing computers was from mathematics in the first place. Yeah, so that's just a preamble, let you go. lets you know what you like. So as I said before, you know, you've probably, most of you have done Python. It's pretty ubiquitous these days. I don't know what it's like. How about in high school? Were you all programming in high school or no? Who programmed in high school? Just a couple of people? No, okay, yeah. So it's kind of, I hope it's changing. Like it's always a thing. It's always a thing. You hope they would learn it earlier, but yeah. So most people do a bit of, you do Python. Is MATLAB still popular? Anyone doing that? It's got like a death grip in engineering for some reason. They love it. Yeah, I've written lots of MATLAB code in my life. Anyone used R? Yeah. What do you think of R as a language? It's kind of weird. It's kind of weird. I'd agree with that. They're all a bit weird. It's fine. They've all got edges. So yeah, so we've got some minimal expectations. You know, it's fine if you don't have that. Just make sure you're going to lots of the help, like the extra support prac, and making sure you're making use of the consultation time to catch up. But you know, most of you have driven a computer since you were little kids, I'm sure these days. You're all much younger than me. It's like, I guess it's a generational divide of having grown up with the internet or not. You know, it's when I can have very fond memories of like these things progressing as I grew and how bad computers used to be. Very different now. Programming, you kind of get variables. You know a little bit about making a dirty script and you can get that to run. You might not understand about structuring a big program. That's one of the things we're trying to get to by the end of this course, is that you get an idea of how to structure a larger program. Because like one of the things you really don't learn in undergrad is like how to work in a big project. Like that's something that kind of when you get out in the workforce, you got to work out, how do I do this stuff without treading on other people's toes, and people will depend on the stuff I've written, and I can't necessarily even talk to them in the same day because they might live in the US. It's like, it's a thing. Yeah, so we're going to do a little bit about version control systems and a little bit of like professional practice stuff that you wouldn't typically encounter, hopefully. Has anyone used Git before? Yes? You're struggling? Good? Good? Anyone else? Does anyone not know what Git is? Yeah, cool. That's good. That's a version control. So I'm going to talk about that in section 2, but I might give a few hints earlier on. Control flow stuff. So I just showed a bit of that with like if and else and for loops and while loops. Done functions, linked them together. Using a computer, you know how to do that. Is everyone on, I guess most people are probably on Windows. Is anyone not on Windows? That's a smaller set. Who's on Mac? Who's on Linux? Hey, good. I'm on Linux, nothing works, it's great. I have this terror that everything's going to die on me while I'm doing this. It's really good for developing in though. So you got the best experience for setting up Julia of anyone, and you'll have the smoothest journey through. We'll end up setting you up with command line tools that are Unix-like to make it easier for you. Yeah, and you know, second year maths, I guess most of you, I assume. Yeah, so you've done a bit of stats, you've done a bit of analysis and linear algebra and calculus. Yeah, that's where we're assuming you're all at. And again, completely understand there's the bimodal distribution of the people coming in here. Some of you have not done much, some of you have done way too much. That's fine, both are good. It's all about getting there by the end. So somewhat loaded picture here. I like to talk about the history bit of this bit. I'll go on this bit and I'll take a break in about 10 minutes, but I'll waffle on like an old man about history. So what is a computer is the first bit to say. And I have a few pictures I like to show for this bit of the course. So this guy. So a computer is, you know, an abstract concept. And for the longest bit of history, computer was actually a job title. It was a person. They were doing mechanical computations with the aid of analog adding machines and stuff. But it was actually a job title, and often women. And interesting bit of history is that like a lot of the early computer programmers were women. Like Grace Hopper is like fundamental one that maybe you would have heard of. But coming from this thing, doing these big scientific projects. It was actually a job title, but goes back further than that. So the idea of what a computer is like, it's pretty broad. I think we said, a computer is a machine that can be programmed a sequence of arithmetic or logical operations automatically, but there's this broad scope of what computation is. I think you can think of not one of these, but a mechanical watch is a type of computer. It's doing modular arithmetic, right? It goes like 60 seconds equals 1 minute, 60 minutes equals 1 hour, 24 hours equals 1 day. You see a bit of the base thing here. God knows why Babylonians chose base 60. I don't know if anyone I don't know why they chose base 60. It's kind of a weird one. Base 24 for hours is probably for the zodiac. We've chose base 10 for our counting because we've got 10 phalanges. Computers don't tend to do that. They tend to be zeros and ones, but it's a machine that can be programmed a series of magical operations. Yeah, so there's a long history of things that you might not think of as a computer that are actually a computer. I like this one too. Does anyone know what this thing is? Seen that? It's found in a shipwreck off Greece. Do you know?
I've seen it before.
Seen it before. It's called, yeah. Yeah. So that's the Antikythera mechanism. It was a calendar, a solar calendar, a mechanical solar calendar that's like 2,000 years old. So like, where are the positions of all the planets and where is the sun at this date? So they had a mechanical machine for working this out 2,000 years ago. It's like they could make a thing like that. Who knows if it actually works? It's a rusty thing in the bottom of the ocean, but they didn't actually know what it was when they found it. So there's a long history of these things. I like these guys. When I was younger, I lived in Japan for a bit. These things are called karakuri. They're automatons. They're little dolls that are clockwork, and they'll write names and they'll serve tea. So there's these complicated clockwork mechanisms inside them for doing these like robotic tasks. So this is another type of computer, an analog computer. Yeah, they're cool. Started getting serious with things like Charles Babbage. Has anyone seen this thing before? This is the difference engine. He was a kind of a very creative guy and dreamt up things he couldn't make, but this was something he actually made. Bizarrely, what this thing was for doing interpolation of polynomials. So you set the polynomial coefficients, turn the crank, and it spits out what the interpolant is. So if you can imagine that, that was useful back in the days. I'll just hold it up for the class, but you can come and look at this when we take a break in a couple of minutes. It's kind of hard to, this is why Andy said he came to this lecture, because I got to bring my old book. It's kind of hard to imagine where we are now, how difficult things used to be. This is a really simple book, but it was for shopkeepers. And does anyone know the pre-decimal currency in Australia was pounds, shillings, and pence? So something you might not think of is if you go into a shop and you say, I need 3/4 of 8 pounds, 3 shillings, and you're like, oh God, what's that? So it's actually a book that tabulates, I'll hold it up here, for this page in particular is 3 shillings, 6 pence and a quarter, and it has all the fractions of how much change you're supposed to give. So if you're a shopkeeper and you go like, oh God, what do I have to do? You can look this thing up. So this is, I think it's, yeah, 1892. So that's where that one's from. That was a book given to me by a friend. Simple things, you know, it's like this tension in mathematics of like, you know, you need to calculate stuff before we had these tools. So maybe someone's, you know, maybe you thought of this as like, how the hell did people, you know, the Greeks knew about sine and cos and tan. How did they work out what sine of 33 degrees was? You know, back in the old days, they had tables. So this one's from the 17th century. It's a book of sine, tan, and cos for different angles. They had these books that people would use. Yep, that's right. Go look through the book. In terms of more everyday mechanical calculations, this one's kind of famous. I keep wanting to buy one, but they cost like $2,000. It's a Curta. Has anyone heard of one of those? It was like what the engineers on Apollo would have used to do their calculations. It's a mechanical hand calculator. So it's got a series of gears and cogs that let you do addition and multiplication. So one day I'll buy one, but they're really, really expensive these days. Another famous one is infamous one, Norden bomb sights. These were for fire control in World War II. When they flew the planes, you've got to know when to drop the bomb, so you hit the thing. You've got wind speed, you've got ground speed, you've got how far you are to the target. These were an analog computer, so again, gears and cogs to calculate when do you press go, so you hit the thing. Kind of a terrible application, but cool technology. Yeah. So, you know, I think that's where I started. I got this paper as well because I was thinking about the this paper. It's from 1957, so it's not that old. You know, I'm not that old, but it's not that old. This was my first thing I wrote in Julia, was the Monk-Res algorithm, when I was working with Andy at Fugro, probably. Maybe it was before Andy, I can't remember. Just before you arrived. So this is a linear assignment problem. So it's an algorithm, it's kind of famous algorithm for going, I've got n jobs and I've got n machines, and I want to give one job to one machine, and each of them can do it at a different speed. What's the best assignment from, you know, job to machine, if you can think of that as a cost matrix. So this is a algorithm that's a fast algorithm for doing this. And when you read the paper, it's very strange because you go like, the notation saying, oh, mark this column, prime this thing, mark this thing. And you go, why is he setting it out like that? And again, it was for this room full of people. This was an algorithm designed to be implemented by a room full of people. So when he's saying mark and prime these rows and columns, it's not an algorithm for a computer like we think of these days. It's for one of these computers or a room full of these computers to do this operations research type problem. That's where we've come. So computers have come a long way. So again, trying to emphasize here though that this mathematical background is there. It's like really deliberate. Like most of the early applications for this stuff were for mathematical applications. All of these early devices, people were doing it for engineering projects. You know, it wasn't to look at Instagram or anything like that. It was just for doing scientific calculations. That's the origin of computers. So it's a good thing as a mathematician to come back to this because it's what it's for in the first place. Cool. I think that's 10 to 6. I might take a break for 5 minutes so I don't lose my voice, but I'll come and talk. Maybe I can sort out your problem. But if you have any questions, feel free to ask. Okay. All right, everyone ready to go again? We're all good? Okay, so said a tiny bit about the history of this stuff. I think it's super interesting to talk about the history because it's like, it's good to see where everything came from. So yeah, analog computers, the scope of what you think a computer might be is probably a bit broader than you might think. It is even true now. So one of the things, I guess, I think it's interesting to talk about in this course because Chat GTP, who uses that? No one's going to admit to that. Yeah, that's like a new exciting thing. ML applications are all based on specialized compute these days. So GPU computing. Has anyone done GPU computing at all? Like, I want to see if anyone's. No, it's like a big part of my job. That's really quite weird because we've got this bit of special hardware that was for doing computer graphics. It's really good at doing a particular type of mathematical operation, basically linear algebra in massively parallel way that's really useful for doing these types of computations that came up in machine learning when we're doing neural networks. So it's kind of crazy that there's this specialized compute that can be used. But so what we think of a computer is super broad. History, one of these things like, does anyone know who the lady in this picture is? Anyone? Yeah? Yep. Ada Lovelace, what's she famous for? Oh, it's not coming up. Oh, God. How do you see it? You're looking at Zoom. Oh, my God. What did you only do to my screen? That's horrendous. Sorry, everyone. Sorry. Can you see that now? Yeah. Okay. Cool. Okay, again, Ada Lovelace. Do you know what she's famous for? First program, arguably the first program. So this guy, Charles Babbage, showed this thing. He had great dreams. This was a general purpose. This wasn't a general purpose computer. This was a computer to do a specific thing. It was for doing interpolation on polynomials. He had this idea of the analytic engine, which is this crazy thing of like, it's a computer that can kind of do anything. And the insight, though, is that having a stored program separate from the computer wasn't trivial. So this idea of a stored program separate from the computer, and it can then, if you can change the program, you can change what the computer does. That's like it's like an advance. So there was an Italian engineer whose name I never remember, who came up with a method, like an algorithm, and she did the implementation that could possibly be implemented on the analytic engine. So arguably the first computer program. That's pretty cool. Yeah, interesting bit of history. So again, another name that you might be interested. So Charles Babbage is a name to keep in your head. There was also, when I talked about automatons, like these Karakura, the little tea-serving robots. In Europe, there was also people who did automatons too. Some famous ones were from Descartes, and Leonardo da Vinci also made automatons. So little robots that could do little tricks. This name here, so most computers today implement the von Neumann architecture. Von Neumann architecture, I'm not going to worry too much about that definition, but CPU, memory, slower storage, multiple output mechanisms on a shared bus. That's the big thing with a von Neumann architecture. Does anyone know who von Neumann is? That should be a big name in mathematics, right? So computer scientists try and say he's a computer scientist. No, he's a big deal in mathematics. So that's another name. This guy here, this one's another famous face. You might have heard of him. Might know who this guy is. Alan Turing, yeah. So he did a lot of stuff. Again, great mathematician. His insight was to do with solving the halting problem. He came up with a model for computation that you can do analysis with, called a Turing machine. Yeah, so it was to solve a maths proof, but he ended up working on early computers as well. This stuff, all these names like von Neumann, Turing, Babbage, they're all mathematicians. So like all of this stuff, all the early history of these, general purpose computing, it was for solving maths problems, and mathematicians were heavily involved in the development early on. Computer science is sort of split off as its own field and kind of run away, but as a as a historical motivation for mathematicians learning programming, it's like you definitely should, because it's always been that way. Yeah, I won't talk too much about that. That's just historical stuff. Any questions on that? That's fine. That's my motivation for you for learning this stuff. So interesting stuff about culture in programming and who a programmer is. And this is like my career. You know, I did my academic career whilst I did undergrad in maths and physics, did a PhD, did a postdoc for a while. Then I went out and joined, I went and worked in a startup for 7 years. That was where I met Andy, doing remote sensing. Then post that another startup and then another startup because I'm an idiot. I don't know what's wrong with me. But so yeah, I've worked in a bunch of different places. Software development has its own culture. A lot of it's to do with this thing, stuff you won't quite get yet if you're new to programming, but this will make sense later on if you come back to this stuff. So I've got two famous quotes here. Code is read much more often than it's written. That's really true. Like when you're a student and you're learning programming, you know, you just make these disposable scripts. You know, you're making something that's basically, you're going to throw it away at the end of it. You're just doing it to get an assignment done. It's not the way when you're out working. It's like you get haunted by things for decades. I still have things that I wrote over 10 years ago that are getting run in production at places. I found out recently. I was horrified because there was stuff I wrote when I was in my 20s. It was terrible. It's still making people money, so whatever. Yeah. And the other one is there's only two hard things in computer science: Cation validation and naming things. It's like you might not get that one. The Cation validation is kind of like, is a really tricky problem, but naming things is kind of the bit I'm trying to say to you guys. It's like, what I'm pointing out here is that a lot of the stuff with this is a communication problem. Don't think of code as, you know, my background particularly, I'll say this, is like I was very results driven. Like, you know, you're doing the program to make the thing. It's never done. Code's never done. So there's a communication component to it that's really important to think about. You try and be clear in what you're doing so other people can read it and understand it. It's really important. And it's like, I'm saying this stuff, you plus, you know, 20 years or so. Coming out, you get these complaints when you have software engineers working with your mathematicians. They'll call them something like a machine learning engineer or something. They always give a new name for people, but you can write stuff that will be very difficult for other people to follow. If it's very maths heavy, they won't follow what you're doing. They won't understand it. So, you know, think about this communication piece early on. So it's even good advice for when you're doing assignments and stuff, you know, make it, when you're writing it, don't think about just trying to solve the problem. Think about how you're communicating what you're doing as well. So make it easy for people to understand what you did. You don't want to be this black box of code that isn't easy to follow. Pot, kettle, black. I'm telling you this, I don't do this, but I'm a very bad offender. It's same as like, so in academia, it's like, think of software as an artifact of doing research work. It's like your currency as a professional academic is, one part of it is teaching, the other part is research, and the currency of research is papers. You know, you publish these papers. So anything you might do is a side effect. That's changing. It's probably more true when we first wrote these course notes than it is now. It's getting better. People are sharing code, so you can reproduce research. That's the reproducibility crisis is a big deal. You know, if you know, it's actually what you did. If you're thinking about mathematics, it's like, you know, part of being a mathematician is being like super clear. It's like you're being very detail oriented about your sequence of logic when you're presenting a result. It's the same in code. It's like, this is actually what I did. It's the implementation. So, you know, maybe you should flip that around a bit, and code output as an output from academia would be a really cool thing. And lots of people are doing that these days. Julia itself came out of MIT from someone's PhD project. So that's cool. You know, and, you know, don't, you know, I'll say this one now, don't undersell yourself when you go out. Like, you'll provide a lot of value. You'll be able to do stuff other people can't do. So that's really valuable. And communication is important. I don't know how much we're going to be able to test in this course, but just a life advice from an old man, like, learn how to talk to people and learn how to communicate, because it's going to be a bigger part of your job than you ever think it will be. Anyway, that's a bit of culture stuff. Cool. All good? All right. Okay, so we're going to start from the bottom, I guess. Okay, we're going to start with a computer basically is a bunch of switches. You know, it's got a voltage that's either high or low. The big revolution between analog computers to digital computers is this transistor thing. It's the idea you can have a switch, right? Like you have a binary state. So the fundamental thing in computers tends to be a bit. So physically what this would represent is on a register somewhere in a computer, there's a voltage that's high or low. You can interpret this as true or false. You can interpret it as a kind of number too. This thing of like, what does this bunch of symbols actually mean is kind of a bit deep, but the fundamental thing a computer works with is bits, right? And logical operations. So what we're going to try and build up to is like, how do we go from logical operations to things mathematicians would care about, people would care about? How does that actually happen on a computer? A bit is the fundamental unit. The abstraction, we won't pretend we're, you know, electrical engineers might worry about this, about solving what the voltages are actually doing through the hardware, but we're just going to go, at our level of abstraction, it's either 1 or a 0, and we can do logical operations on it. So a bit is a 0 or 1. That's that first bit. Now, the next bit is a byte. This one's confusing because it's not always been true. It's the thing that people have kind of converged on as the truth. A byte is 8 bits. Used to be like 5 or 6 or sometimes 7, they'd call it a byte, but they kind of standardized over time and now it's 8. This is like really early on, like if you're talking about in the 40s and 50s, they didn't really have these units. They hadn't all sorted out. So tends to be another thing that comes along is a byte is a sequence of 8 bits. So if you can think of, you know, 0, 1, 1, 0, 1, 1, blah, 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 you have 2 to the 8 options when you have 8 bytes. So that's a simple thing. So if we're thinking about, first thing we might care about as mathematicians is the natural numbers. So how might we represent natural numbers in bits? Has anyone come across this before, or is it all new? How do we actually represent the integers? What's the obvious thing you might do? Base 2, yep. Cool, so that's loud. There's this encoding problem. I'll wait for that to pass. There's this encoding problem, like we could choose any representation to be, oh, thank you. We could choose any representation, but there's a sort of natural one to go, we're just going to count up. We're going to go 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, blah, 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 all the way up. So it's called an unsigned int because we're worried about the natural numbers. So in Julia, if you want to make an unsigned int, uint, really helpful thing to do in Julia, it's a bit hard to see what I'm doing is if you see anything in the notes like a function or a type, talk a bit more about what types are in subsequent lectures, but I'll keep hinting at it today. You can do shift ? That will put help. You can type uint 8, and it will say an 8-bit unsigned integer type. Okay, so any of these things I did before, like sum, you know, if you see that, it will give you a help string. So that's a really useful thing to do. Just so, you know, shift ? Type in whatever your thing was. So uint 8. So if I make 2 and I've turned it into a uint 8, you get this funny little string. But okay, so uint 8, you only get, if you've got, it's not often you only have 8 bits on a computer these days. 8 bits is pretty small. You only get 256 options in that range. So your dynamic range is pretty small. You'll come across this though in image formats. They'll be saved as uint8s in JPEG, PNG, typically 8 bits because our dynamic range in vision isn't very good for color. So we can only see, you know, they figured a while ago that that's as much color depth as you'll be able to make out the difference between. So that's all they store when they store it in an image. That's a uint8. Now things get a little bit weird. Was like we might care. So just as you have uint8 though, I'll just say you have uint. So if pressing tab, you'll see these different size uints. So unsigned integers, you got 16-bit, 32-bit, 64-bit, 128-bit if you want. So if you want to go really high. So that's it. Things get a little bit more confusing though, when you might worry about the bit representation of signed integers, right? So if we care about a sign, what would be the dumb thing to do? Like, if you're like me and you're not very smart, what would you do for representing the sign?
You could start by counting like negative 1 through 7 as 0, 0, 0.
Yeah. Anyone? Oh, yeah.
Also have like the last digit as your sign.
Yeah, that's right. You could have that. So the bit encoding, you could also have a sign bit at the front where you go like, it's just 1 or 0 if it's plus or minus, and then you do what you do for unsigned int. What I want to kind of point out here, and this is, I'm going to apologize a little bit if the lecture goes from like 0 to 100 for some people really quickly, but this is kind of deep. We can see there's a bit of Julia code here. I'll say the first one is what this code does. We're going to go, to walk through the syntax really quickly. We go for n in 0 to 255. All this stuff here is just for syntax. So you see how this code, this output has this ellipsis through here. That's just going like, oh, if it's between 0 and 18, or it's greater than 250, we're going to print out the results. Otherwise, we're going to print some dots. That's what that little bit of control flow does. So it looks a little bit more complicated than it actually is. It's just because it's a little bit of formatting for the nodes. Another little thing you might see here, I'll just quickly do the syntax, is you can do /le, and then I'm going to press the bit you can't see is I press tab and you get less than or equal to. And this will be a function like anything else. So this is less than or equal to. If you want some Unicode stuff or some cool functions, Julia lets you do that. Yeah, so what we're going to do here is we're going to print out this bit string. So you know how I said when I did this here, I went, okay, uint82. We're getting this funny OX02, and that's actually saying the X bit is saying it's in hexadecimal. It's cast at hexadecimal. So if we want to see what the bits are, you type this bit string, if I can type uint8, it will make a string of the bits. So for uint8, it goes, if we're going to go 0 is all zeros, 1 is 1, 2 is 10. To the death. That's basically all these things going through a loop and doing that. It's also putting out the hexadecimal value. So we'll talk a little bit about hexadecimal as well. Hexadecimal is this useful thing of like a base 16 thing, because it's like you get 4 bits together. It's sometimes useful to have it in this form. So that X is if we're doing hexadecimal. So if you go OX1, you're going to get a hexadecimal number for 1. If I want to cast that to an int, you'll see what it is. It's 1. Hexadecimal goes, that's 10, 11, 12, blah, blah. So that's hexadecimal. It's useful sometimes looking at binary formats. People who've done low-level coding, they'll see hex dumps and stuff all the time. I'll show you one of those in one of the subsequent lectures. That's just what that means. So we're going through here. You can get this thing by showing it in base 16. You can do string. And let's just check that syntax, make sure I'm not lying to you. Yeah. So you can go 2 base equals 16. And if I go, what's 10? Should be A. So that's that equivalent. If you wanted to type it in directly, RXA. Is that clear? That's just a bit of Julia syntax. This is like, you don't tend to do this very often, but we'll show it to you in this course. So make sure I hammer into you that that's what this is, because you're guaranteed Yoni's going to give you a quiz and it's going to say something about this and you'll go like, oh God, what's this stuff? But that's for, you can do an equivalent one for binary. Oh, if I can type, that's in binary. So for B, yeah, anyway, you get the picture. So this is the encoding. The thing I want to say is this is a choice that someone's chosen to represent unsigned integers this way, in this natural way where you go 0, 1, 1, 0, blah, 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 blah. Immediately, if we go to signed integers, you might see something a bit funny. So hopefully this is clear. So this is to represent negative numbers between minus 256 and minus 128 to 127. You'll notice that, it's not doing the sign. It looks like it might be doing the sign bit, but they count up from the bottom once you do that. That's pretty weird, right?
Is the last digit essentially like minus 1, 2, 8?
What's that?
Is the last digit pretty much representing minus 1, 2, 8?
Well, no, it's representing 0 in this one. So if you look at what 0 is down here, it's 0, 0, 0, 0, right? So it's like counting up from the bottom until you get to 0 and then counting up again. Yep.
So you use the same axis for iteration.
Okay. I'll show you this. This is a bit where I'll sort of apologize because the lecture might go a little bit too low level. This is a point, it's a kind of a didactic point I want to do for this lecture is like one of these things when you come from maths to computer science, not that you're doing computer science, but you're getting a bit of it, is like when you do abstractions in mathematics, they're perfect. When you do them in computer science, information about low-level stuff always leaks through and pollutes what you're doing. And I'd say this is one of these cases. The idea is, we've got a bit about hex here. Yeah, so hexadecimal, yeah, I'm going to come back to this though. Just stew on it for a bit. It's one of these cases of the abstractions of how this is actually implemented in hardware is where it's coming from. I'll come back to that in a bit. So that bit will be a little bit complicated. So if I lose anyone, I'll come around and back. So as we said, hexadecimal is super common. Hexadecimal uses 4 bits. Prefix notion OX, if you want to write hexadecimal. Again, I hope that's pretty simple. Cool. So yeah, I think I did all that stuff. That's hex. I don't know how much I can say about that. So has anyone watched Silicon Valley? The show? No, I'll always leave that one. There was a joke on that about what's F times 9, but it's not 75. Anyway. So this prefix notation is the thing I want you to take away. So if you want to represent a binary number, you can do 0, 1, 0. So, oh, maybe that one. So if I write that binary number, does anyone know what's that going to be? So, yep. 2, 0, 1, 0. So again, what about this one? If I go up to the next one, what's that going to be? 4. So 4, and what about the next one? What's this pattern that's coming through? Yep. So when you're doing binary, you end up counting in powers of 2. It's basically, like 10, 100, 1,000 is going up, powers of 10. In binary, it's powers of 2. In hexadecimal, it's powers of 16. I'm not so good at that. Another hint for hexadecimal is if you need to count, you can count 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7, A, B, C, D, E, F. You've got 16 on these fingers if you need to do it on your hands for whatever reason. Okay. So yeah, you can do, this is what I'm trying to say. What I'm trying to get at here is we can say, this is a good one to demonstrate. So we can go, yeah, let's just do that one. So x equals 11. And we've got the binary representation of 11. So equals equals. So this is the thing, if you're new to programming, some people will get confused by. Equals is assignment. Equals equals is logically equivalent to. There's also an equals equals equals, which is identically true in bits. So if we're going to go the binary representation of this, B1011, that's true. So that's just different representations of the same number. So if we do this thing in hex, that's the hex one, is it B? True. So they're just different encodings of the same number. Not so interesting. I don't know how much to say about it. I feel like I'm harping on too much. You can add these things together. So you can go OB101 plus OXB. If you want to know what that is as an int, you can do that. 16. So, cool. You can do multiplication, division. Cool. That's not going to work. Anyone know what's happening there? Nope. Yeah, it's not an integer, right? So if we wanted to do that, so float 64. Yep. Okay, cool. That's just basic arithmetic stuff. You're seeing a bit about data types too. So natural numbers, ints, integers, unsigned ints is kind of the model. It's going to be some stuff weird stuff that happens though to do with the implementation details of this stuff. So one of these ones is wraparound. So if we've got a uint 8, and we said, you know, this is the max of the range to this guy, right? That's OFF. What's going to happen if I add 1 to that? It's kind of a bit surprising, right? Any predictions of what's going to happen? Unsigned, it's an unsigned int, so it can't be negative. You go back to 0. Yep, so it comes back around to 0. So one of these things that will bite you because we're using a finite amount of precision to model this thing. You've only got 8 bits in a uint 8. If I did uint 16, will this happen? So I've gone up to 16 bits. Is that still wraparound problem going to happen or not? No, we're fine. But you can't tell what it is because it's got this stupid hex. 256, that's fine. But if you went to, so useful function in Julia, surprisingly useful, uint 8 will tell you the biggest value you can have as a uint 8 is type max, 16, you got way more. So anyone can do 2 to the 16 in the head is 65,535. So you can get up to that big. So depending on what you're trying to do, you can get bigger. 32 bits of precision. This was a famous thing in Windows. It only had 32-bit operating system, so you couldn't have more than 4 gig of RAM because 4 billion. Couldn't address the memory. So that was a thing that happened. Now everyone's got a 64-bit operating system, and we hope we'll never have that much RAM. So that might come back again. But 64 bits, 2 to the 64 is a very big number. Yep, not going to happen. That's through an error. Yep. So that's an int anyway. So we want to do big int. Anyway, blah, 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 blah. Yep. The default type for ints, I should say that, is 64-bit. Oh, type max. Yep. That's a big number. Okay. So yeah, that's the thing. That's limitation. So this wrapping is definitely a thing. And wrapping of signed integers, you get a similar thing. So if you add 1 to the signed integers, you end up background at the bottom. You go from 127 background to the bottom. Okay, now this is the bit I'm slightly going to apologize for. We'll go to not to 100. I'm scared. Okay, you guys are all fine with this one though. Okay, so on a CPU, I'll just get oh, I've got notes here from you before. Hey, cool. That makes it easy. So hopefully you're familiar with logical operations. If I've got two data values and they can be bits, I can say, everyone happy with and? If I say and, if I've got this is false and this is false, A and B is also false, right? Everyone happy? A is true, B is false, A and B is false, blah, blah, blah. Similarly, symmetrically, if this one's true and this one's false, false, and if they're both true, that's true. So on a logical circuit, so this is when out of maths back to the real world of engineering and how things are actually implemented, what CPUs can do is logic really fast on registers. So they can take a series of bits and do logical operations on them really fast. So the question is, how do you add 2 numbers? So how would you add with logical operations? And maybe this is obvious if I do a, so if I do I change this guy. No, it's not going to let me. Anyway, I think old version of Excalibur. So if I do an OR, 0 or 0 is 0. Oh, sorry. False or false is false. False or true is true. True or false is true. True or true is true. That's the series. There's this thing called an exclusive OR. which is like, yeah, that, but not the two case where both are true. And if I'm thinking about this operation we were just talking about of addition, what does that look like?
The digit that you get out of the column.
Yeah, so if in binary, if all you've got is zeros or ones, so 0 plus 0 equals 0. 0 plus 1 equals 1. 1 plus 0 equals 1. 1 plus 1 mod 2 equals 0. Carry the 1. Make sense? Did I lose anyone there? Good, good, good. So with an exclusive OR, you can add 2 bits. So what I've got here is this thing called a half adder. So I've done this. This is more Julia syntax that you want to see. There's something here. I've done these two colons with a T. That's called type annotation. This, you don't need to do this. I just did it so you see a bit more syntax. Sometimes you do need to do that. And this is like one of these cases where Julia becomes really useful, because it is a typed language. We'll say a bit more about that later. So I'm going to take 2 numbers, A and B, where the type is a subtype of the Booleans. So that's what we're talking about, bits, true, false values. And this equals XOR A or B. So in terms of the carry bit, let's think about that one. If we're plus adding 2 numbers together, what's the case where we need to carry 1? When they're both 1. So that's equivalent to logically AND. So that's right. So this is a little thing called a half adder. Let's copy this across. If I go half adder. Oh, simple. Sorry. Okay, so we can see if we're thinking of, so in your head, think false equals 0, true equals 1. What's false plus false? Is going to be 0, carry 0. False plus true is going to be true. 1 plus 0 is, 1 carry 0. And same symmetrically the other way around. True, false. That's the same. So it's going to be 1, don't carry anything. And if they're both true, it's going to be false 0, carry the 1. So that does, if you think of your bits as a string, if I had 2 numbers like A equals 0, 0, 0, 1, and B equals 0, 1, if we just take that last column and we're just adding those 2 together. So the way to do a way to do arithmetic is to do what you learn in primary school, but you just do it on binary. So, you're going to write out the 2 numbers and you're going to go this plus this, this plus this, carry the thing all the way through. That primary school addition algorithm is what you can do on a computer. And the thing is, you just do it with logical operations because you're dealing with Booleans. And the first bit is this half adder. And a full adder, this is the exercise left to read a bit. You can show, so this thing I was drawing up here, this is always a problem because it steals my focus. This thing's called a truth table, where you just go like, here's my inputs, here's my output, enumerate all the cases. If you do this for addition with a carry bit, so if I've got an A, a B, and a C, and you work out what you're going to do on the next line over, if you go over. So for the first line, you can just do this half adder. Then when you've got a carry bit, you've got to go like, what's 0 plus 1 if I've carried the 1? Do all those cases. There'll be 8 options. You can show that you can make that from 2 half adders. So that's what this function here is called. It's a half adder. So I'm going to go iterate through my bit representation of this thing one at a time with a possible carry bit. So I've got 3 inputs this time. And I'm going to do half adder, half adder. So this is useful to know you can construct it this way, because if you're making an actual circuit, you just have to make a half adder. You just need 2 of them. You can wire them together and then you can get a full adder. So what you get is you take this, take the output of that, pass it into the next one, and what you get for the next one is carry A or carry B and this thing S. That's called a full adder. Hopefully that's clear. And that's how, if you take this and you iterate through, that's what this next little bit of code is. We're going to add n digits together. So AB, and calculate A plus B using array indexing and logic operations. So we've got a bit more here to go through. So what we do is we're going to take two integers. So I might copy this function across and just pull it apart a bit so we can see what it's doing. Again, this isn't something I'm going to necessarily expect you guys to follow 100%, but it's a good explanation of like, why did they pick this weird representation? This is the reason why. So not clear yet, but we'll get there. So we've got this function add n digits takes two numbers where A and B are subtypes of the integers. So we're going to go like A equals 12, B equals 15, or 1, because my 5 doesn't work. Okay, next bit is this digits function. So we're going to convert. So let's say pretend n is where we're working in base 16 or base 8, whatever it was. Oh, we're going to go base 16 because I picked big numbers. Oh, no, base 8. Okay, so this is instead of that bit string function. It's just a different way of doing it. Instead of making a string, I made an array of vector bool with this digits function. So A was 12. You'll see, instead of getting this giant thing, so we've got, it's only 8 bits long. So we've got 0, 0, 1, 1, start to finish. Hopefully you can see that's the same thing. And similarly, for B, we're going to get this array of 8 long. That's, you know, that thing we said was OX. That should be, oh no, what did I do? Wrong way around. B's base is 15. Oh yeah, sorry, yep. Anyway, blah, blah, blah. Anyway, digits function is just showing there's two ways to skin a cat. So like you could do this bit string thing, you couldn't do this digits function, they both do the same thing. If you're confused what it is, ask for help. It's basically a way to convert between one type and another type in a given base, padded with zeros of specified size. Okay. So what we're doing is we're going to turn our integers into a string of bits. And what this is like, this is a software version of what gets implemented in hardware when you're doing addition of integers. So you have this low-level circuit called a half adder that you can make out of an XOR and an AND. You have a full adder that can be made out of two half adders. You you have a finite register, you might have 8 bits, you might have 16, 32, 64. You're going to turn it into the Boolean representation on that basis. And then you're just going to iterate through one at a time, applying the full adder to the ith element in the array. So what this little bit of syntax is, if I have an array A equals 1, 4, if I go, now this one for everyone coming from Python sort of annoys a lot of people, but one-based indexing in Julia, lots of people get mad. But so the first element, we'll just say it's like first, second, third, fourth. It's actually a more complicated story than that. There's actually arbitrary indexing. So you can just go first of A as well. If that annoys you too much, it's probably better to do that than to do the array indexing. But basically we're going through this array. We're going to get the Boolean of A, Boolean representation of B, and the carry bit. And we keep applying this carry. And this, the whole point of this is a long-winded thing. This is like too much detail about something that's probably less interesting. But the whole reason we have this weird representation that we talked about back here, where we go like this is called 2's complement is the name for this. And the whole reason we do this is because we can use the same circuit to do addition for uints and unsigned ints and signed integers. The same circuit works for both. That's the whole point. So it's a weird representation. You know, you could, the obvious thing to me would have been to go like, oh, there's a sign bit out the front, and you just do minus that. You need two different circuits to do addition if you do that. Whereas if you have 2's complement, you can use the same circuit to implement both types of addition in hardware. So we're trying to be super fast. This is a kind of a ridiculous thing to do. What I've done here is in software implemented what they do in hardware anyway. They don't even do this anyway. But the whole point of this is that if I take, and hopefully this is what this demonstration is, you can see why this wrapping happens is the first thing. And you can also see that you can get to use the same circuit to do unsigned or signed integers the same way. Is that clear? Long story, maybe that's probably lost a few people, but that's okay. Come back to this one when you've done a bit. I would encourage you all to pull this apart. Like, as I was saying at the start of this thing, it's like you can't learn this stuff by looking at it. You got to follow through the logic. Again, big takeaway points is that for binary, XOR is like doing modulo 2 addition. So that's that thing. How would you implement this thing in circuitry? Here's a thing you can do. This thing in particular is called a ripple adder. I hope you can see visually why that is, because you're rippling through the bits. Okay, now, one of the things that I'm interested in trying to convey for this course for you guys is like an algorithmic approach to thinking about stuff. Like, particular applications not so interesting, but the algorithmic thinking is the thing we want to imbue in you as you start to think of this stuff. So you could, does anyone have an opinion about, is this in terms of circuits? Like if I was making this logically, could you do this with less circuits? Is that's like, there's an idea of computational complexity for circuits that's like so-called circuit depth. Could you do this in less logical operations than what's implemented here? Do you think this is the most efficient implementation of this addition? You think it is? Anyone else? Is there a reason to work through it one bit at a time and do this ripple through? Could you take chunks of bits and do the same thing where you're effectively operating on a different base? That's one idea. So this is one of these things where it's another thing I want to try and convey when we're doing this course is that computers are a pile of abstractions that aren't great, but yeah, what do I want to say about that? So yeah, what actually gets implemented? You can think about addition on a CPU. It has an arithmetic unit that's for doing this sort of low-level arithmetic really, really fast. What Intel or AMD do on their computer, I don't actually know. I probably would struggle to understand. It's probably some hyper-optimized version of this thing that's like taking chunks of things and interleaving them together to make this with as few circuit components and be as fast as possible. So that's an interesting thing. So try and think about these things. So that's addition. The next bit I want to point out is like, I said, basically what we're doing here is the primary school version of adding, where you go like this plus this equals this, carry this, blah, 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 blah. How many operations do I need to do to calculate that based on an input size of n? Order. Does anyone think about that? Like how many times do I have to go? How many times am I going through this loop here? Sorry, say that again. N times. So it's linear in the size of the array. So if you could do more operations at once, you might be able to reduce the amount of complexity of this operation. The next one to talk about is multiplication, right? So what's the primary school multiplication algorithm, if anyone wants to think of that? How do you learn to do primary school multiplication? Oh, you could do that. That's one thing. What's the algorithm though, if you think about how you learned to do it as a kid? Multiplying integers, yeah. Yep, and then do it again. Yep, exactly right. So if you think about the computational complexity of that algorithm, primary school multiplication algorithm, how does that depend on the size of the input array? N squared. Is that good or bad if we get to big N? What's that? Bad, yeah. So this is one of these ones, it's like what actually gets implemented isn't for multiplication because that becomes a problem. There's particularly when you get to big integers. So we talked a little bit about types. So there's a whole bunch of algorithms and the one I think is, what's the name? I'm going to get the name wrong. Karatsuba's algorithm, I think is what it's called, is the algorithm for doing multiplication in integers, and that's actually n log n. So we're going to talk more about that computational complexity. Section 2, I just wanted to kind of introduce it here. So you think about like that naive thing I do of like going this times this, this times this, this times this, add the 0, blah, 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 like you said, and then add them all at the end. Might not actually be the best way to do it. You might be able to rearrange these things to do it in a better way that uses less operations. And that's most of the game of doing algorithmic software development. You're trying to make things faster. You have an algorithm you want to implement. You're trying to work out, how can I do this in as few operations as possible? And it might seem sort of like a silly game, or it's like you might have to wait a bit longer, but depending on the algorithm you're running, this can be a huge deal. And making fast code is a big deal. It's like why work in Julia, because it's a fast language. It has, I was talking about ChatGTP. It's like I was reading recently to ChatGTP is based on GTP 3.5, I think. And I think the estimate was 75 tons of carbon for one training run. If that sounds, that's like a household for 2 years or something, I think it was, for one training run. So all these companies are doing these large ML models running like that. You compare it to internet traffic, what gets implemented has these long-range consequences in terms of energy use and efficiency that you probably don't think about. So it is actually worth thinking about these things, and it's non-trivial how much it's going to play. Computational complexity and these things are really important practically, even unless it's too hard to actually work out. So that's kind of a hard one. Okay. Now, again, here's the easy way of doing multiplication. Well, I'll go back to this one. So hopefully I didn't leave you too much there, but that's a taste of things to come. I'd encourage you to come back to this bit later on in the course when you've done a bit more and you look through this code and go, hey, Paul, you did that bit wrong. Figure it out. Okay. We were talking about binary and powers of 2. Let's make a binary number, OB101. Okay. And if I do bit string X. Okay. So as I said before, let's do this one. So we go, okay, we did 1, then we add a 0. We see what's happening to, if I look at this line and this line, sorry, just trying to highlight this one. I've put 4 in as a binary. We can see it has this bit string representation, and we've got this one. This is 8, like we said, powers of 2 for every time you go up in a 1. That's this guy. What's actually happening there? Like if you think about this. Sorry? A shift. Yeah, so this is like super simple to do in hardware. Like you can just take a register, shift it across by 1, shift it across by 2. That's a super fast operation, and this is called a bit shift. So this is something you can do. The syntax for this is these 2 arrows. So you can bit shift this way. Oh, not 3. So I go that way, or I shift it that way. In terms of what, remember, X is 8. So if I bit shift this guy to this, what's going to be the effect? What's that going to be? What's the answer to that guy going to be if I bit shift it to the left, to that direction? Right. What's it going to turn into? Well, if I bit shift it 2 more, 2. Same the other way. If I bit shift up by 2, what's the answer going to be? It's 8 to start with. 2 times though. If I do it 1, it'll be 16. If I do it 2 times, 32, cool. So this is like a super fast way of doing integer division by 2. So this is like, when you do, we'll talk about this in the next lecture. I'm going to go through some applications to some more mathematical types of functions you might want to do. This is a nice trick to know sometimes if you have an integer and you want to divide it by 2. Of course, you know, if you have a thing that's not going to evenly divide 2, you're going to get the effect of rounding. But if you need an approximate divide by 2, it's a really fast thing you can do. I don't think in real life I've ever had to do this very often, but I'll show it to you in this course because we're starting from the low-level stuff of bits and what these operations might look like. So I intentionally haven't shown you multiplication because it's actually really hard. Addition was kind of hard. Multiplication is like another order of magnitude. That's, because this tension between algorithmic complexity starts to come in. So that's a bit shift. Hope that makes sense. There's a couple more examples there. So this one is a useful function in Julia. Again, this will lead you astray if you use it on more complicated types. I haven't really told you what a data type is. I realize that. We've just talked about uints. That's an idea of a base data type. There's unsigned ints, really how you operate on these things. Julia is based on something called multiple dispatch, which is the function you apply depends on the type of the variables coming into the function. I'll talk about this a bit more later. This will be more obvious to you later on that this is useful. Anyway, so size of will tell you the size in bytes of the canonical binary representation of given data type. So that's what we're showing over on the left. If we've got x equals an int 8 of 120. So int 8 is a signed integer with 8 bits. How big do you think that's going to be in memory? Anyone want to have a guess? Yep. 8 bits, 1 byte. So, okay, so if I did a 16-bit integer, what's that going to be in bytes? 2. Yay, you're all on top of it. Cool. Okay, 64, oh, there's not a 4. My keyboard's a bit terrible. 8. Yeah, 64 is the default in Julia, if you don't say. So if you go, so that's equivalent to saying if I just go 120, x equals 120, you don't really know what that is. Really useful function in Julia is type of x is an int64. So if you don't say, it'll go to an int64, unless you're on a 32-bit computer. Some of you might be, I don't know why, but you might have a really old computer, that's fine. So if I do size of x, if I just say, if I don't do that type constructor, and I just go 120, it's gonna be 8. Okay, cool, strings. This is gonna be an interesting one. Does anyone want to guess what, this is a string. So if we're doing a string of characters, you put quotes around it. So that's to represent characters. If we go hello, anyone want to guess without looking? I can't, I've got to hide it. So again, there's this question of representation, like how the computer decides to represent a string in memory was basically a design committee 50 years ago. There's lots of ways you can do it. So size of x will give you a hint about how it's represented. So it's saying there's 5 bytes. So each character is 1 byte because the length of x, that's this array, will be 5 long. So for example, if I do hello, that's 6 long and 6. It's kind of annoying because it's always 1 for 1. There's this many bytes per character. You can actually index and get the ASCII Unicode character. That's a hint about what's going on with hello. That's the first, that's the last. That's an exclamation mark. Unicode is a particular character in way of embedding characters, representing characters on a computer in memory. So that's the Unicode for that. We've got a few more. So if you, this is this one, if you want to do, so if I want to do maths characters, you can do, it's like all the text strings will end up parsing. So you can go alpha, size of alpha is 2, whereas if I did, oh, that's interesting, right? Because we've got into the extended character set, so it requires a bit more memory to deal with that because it's not in the normal set of characters. Cool, if we've got no, here's a constructor for an array. If I do this thing, again, if you want help, shift question mark help. Ones will initialize an array of all ones of a given type. So what we've got here is ones, u int 8. I'm going to make 1,000 of these guys. And what that looks like is that. So what's that going to be? Size of that? Anyone want to guess? Cool, perfect. And if it was 16-bit, 2000, perfect. And if I don't say, it's going to default to 64, 8000. Cool. Interestingly though, it won't default to, it defaults to float 64. I haven't talked about floating point yet. So that's going to be coming up soon. So, cool. That's what I wanted to show. All right, so floating point is kind of the next bit. So we started today on a computer. All you've got is bits. Don't think about the voltages, you know, it's kind of this discrete system that changes between 0 and 1. That's all you get. You can do logical operations on them. The next question that comes up is like, cool, we've got the natural numbers kind of with some weird edge cases where if I add too much, it'll wrap around and come up underneath me. And this weird thing that the embedding in memory is really strange if I think about it for signed. It does something weird and that's something to do with the hardware. Who cares about that? Why should I need to know about that? You kind of do. The next bit is how would you represent the real numbers? So that's floating point. I'm not going to say heaps about that today because I've pretty much run out of time. But what we're going to go into next lecture is we're going to go through some mathematical functions, do a hello world, and I'll talk through two cool, I think the square roots and factorials are two cool functions that are very mathematical, give you a hint about what mathematical programming looks like. Okay, any questions? Cool. I guess we'll leave it there for today. I'll see you guys tomorrow.